Hi, Dr. Pat here. We're looking at matrices to solve systems of equations. And before we really get into the, hardcore stuff, we want to basically be able to translate between equations and matrices. That's the key thing. I mean, the technology can do a lot of the work for us in terms of actually doing the grunt work for solving our system, the matrices. But basically, we got to be able to convert from the situation, the equations, to a matrices in order to solve it. Okay, so let's do some practice on that. All right, what you see here is I've got a couple of system of equations, two different sets, and basically what we want to do is convert these each to a matrix. Now remember when we're doing converting system of equations into a matrix, basically we're keeping our columns very ordered in a way. We don't want to be mixing up our columns that way. And so we're going to have an x column, a y column, and then that constant number column. And so when we do that, we're just taking the numbers, we're leaving the x's alone because we know this is going to be our x column, this is our y column, and then this is our constant column. And because we're including the constant column, we call this an augmented matrix. Okay. And so then for the second one, hopefully you kind of get the idea here. You might be looking at it like, wait a minute, our columns are all mixed up because of the equations. There's a missing y here in the second equation. So we have to account for that. So when we make our matrix, we got to make sure in that second row of the matrix, we're going to put a 0 in the y column. And that's what you're seeing right there, a 0 in the y column, because this second equation did not have a y in it. And so that's where we're going, just taking the numbers and then keeping our columns pretty all situated. Even if the equation didn't keep the columns for the matrix, it's very important that we keep our columns straight. Okay, and then we can go backwards then, go in the reverse way. So what we want to do here is we have matrix and we want to convert it back into a system of equations. And so you can call this first column your x's, your y's, and then your constant. And so hopefully that's what we get. And now for the second matrix, you're seeing that 0 right there. That's just basically saying that in our first equation, it's not going to have an x in it. It's going to be a 0x. So we don't have to write an x in that first equation. So that's what you're seeing. It's missing the x component because of that 0 in the matrix. And so this first equation, just an equation with y in it. And hopefully those make sense. So we can kind of ratchet up, we can go to a bonus level in a way. And so basically what we're doing here is converting this matrix, augmented matrix, because I have 4 rows, that's telling me 4 equations. I have 4 columns here that will have the 4 variables, and then I have a 5th column which would be then the augmented part, which would be the constant part, would be the equal signs. Okay, so take a moment, translate that, see what we get. Now if you did that, here's the equations that I made. Now the catch here is you can use whatever letters you want as long as you keep your column straight. And so basically I decided to go A, B, C, D, and then my constant column over there. And so you could have done X, Y, Z with a W. So any variation, but the key thing is make sure your columns are pretty straight. Now in this case, the fourth equation that I have here, I have a 0 in the first column here. In this fourth row here of the matrix, I have a 0 right there in that first column. So fourth row, first column, that spot, that's telling me I have 0 A's. So in my equation here, you see in the fourth equation, my last one here, you see no A term in there. So I just have a B term, a C term, and a D term, and then the constant term because of that 0. Because of the 0 in that third row there, it's in the fourth column there, third row, fourth column. That's telling me I have no D term in my equation. As you can see, no D term there. And then for that second equation in the second column, I called that my B column. And so in the second equation, you see no B term. And then in this top row, I have a 0 in the fourth column. That once again means that there's no D term in that first equation there. All right, so now what's so special about this matrix? Now this matrix right here is really, really cool for us. Here's why. Because there's a 1 here in this first row, I'm looking at the first row here. Because there's a 1 right there in that very first position and zeros here, remember that these first 3 columns are the variable columns about the coefficients with the attached to a variable like x, y, and z. It's the fourth column that's a constant. So in this case, what I'm looking at here is I'm translating that 1 in that first column right here as an x. So this statement is really saying x equals 8. In the second row here, that there's a 1 in there in the second column, that's like my y value. So that this row here, the second row with a 0, 1, 0, 9 is translated as y equals 9. When we look at the third row here, because of the 0 in the first column, 0 in the second column, that means we have no x or y. And the third column here is a 1. That's like my z. So that third column, or that third row here, with a 1 in the third column, basically is telling me z equals 5. Now that's a really cool matrix there, because it's telling our goal. It's telling us x equals 8, y equals 9, and z equals 5. It's our solution matrix. It's telling us what our solution is. So hopefully you get this idea as you're translating between matrices and equations, that this matrix is our ultimate goal for all our system of equations. We want to be able to produce matrices like this so that we can quickly identify what our x, y, and z are. I hope this was helpful. Take care and have a good day.